Good morning. This is the first segment of section 1.4, which is the last of, I don't know, it's usually the first chapter in a textbook is kind of review, but I wouldn't say it's necessarily review for everybody. But as you recall in section 1.3, we had developed the definition of the six fundamental trig functions. We developed some identities. And we had also looked at some ways of calculating trig functions for quadrant angles. Now, what we're going to do in section 1.4, which is not a particularly long section, but it's kind of a little disjoint. So what we're going to do is we're first going to talk about a sort of a critical aspect of the SIGN of each of these trig functions. Then we're gonna develop some additional identities which are based on the distance formula, and then we will have some example problems of where we're given some information about one particular trig function, and we're asked to find other ones. So we're now going to, we could go back to the definition where we just find X, Y, and R, and that sometimes is very valuable to be able to do that. But we also want to be able to work with the trig functions irrespective of their definition. And so there are some interrelationships. That's where these fundamental identities start popping up and starting to be relevant. So that's just sort of a big overview. I think this will probably take maybe 3 or 4 segments to cover. But it just depends on how quickly I can get through it. So without, I think, I don't have my document camera plugged in, so we'll shift over here real quickly. All right, so this is, I think I might be a little bit out of focus, so let me just, okay. So section 1.4. Okay, so here's the first thing to note. We talked about the values of the trig functions for quadrant angles, but the first thing that we're going to do is, rather than actually talk about the values of the trig functions, we're going to discuss whether or not they are positive or negative in the quadrants. Now, not quadrant angles, but actually the spaces between the quadrant angles. It turns out that all trig functions have either a positive or a negative value inside every quadrant. They're never 0 and they're never undefined. So it's what we're going to develop is a mnemonic so we can remember what the SIGN of trig functions are based on their location. So let's just recall the quadrants. Remember, we had Q1, Q2, Q3, and Q4. Now, what I'm gonna kind of note here, remember that based on the definition of these trig functions, there will, in many cases, R, the distance from the origin out to some point on the ray, may crop up, but recall that R is always positive. So R, and I'm just going to kind of keep a little catalog here. So R is always positive. And this is kind of critical. So we can maybe just kind of do sort of a shorthand, R is positive. Because when we're talking about signs, it doesn't really matter what the values are, just whether they're positive or negative. And since we're involving ratios, I think you'll see where this goes. So for Q1, note that X is always positive and Y is always positive. And of course, R is always positive. In Q2, note that X is negative, but Y is positive and R is always positive. So we have X is negative, Y positive, R always a positive number. In Q3, things flip here so that X is X is negative, and Y is negative. And of course, R is always positive. In Q4, X is positive, but Y is negative, and of course, R is always positive. So X is positive, Y is negative, R is always positive. Okay, so based on this, let's just kind of think about a particular function. So let's consider sine for a second. Well, in quadrant 1, sine is y over r. So sine is positive in quadrant 1, positive in quadrant 2, negative in quadrant 3, negative in quadrant 4. What about cosine? Well, cosine is x over r. So it's positive in quadrant 1, negative in quadrant 2, negative in quadrant 3, positive in quadrant 4. Okay. What about the reciprocals? Well, for any function, if it's positive, then its reciprocal is also positive. And vice versa. So really, we only need to know sine, cosine, and tangent, and then understand that the reciprocals will have the same SIGN. So let's look at tangent. Remember, tangent is y over x. So in quadrant 1, tangent will be positive. In quadrant 2, it will be negative. Quadrant 3, it actually flips back to positive. And then in quadrant 4, it's negative. So if we were to kind of create a very complex graph, we could show, which ones are what, wherever. But it's easier sometimes when you're memorizing these things to just create a mnemonic. And there's a very common one that's used in trigonometry to be able to, and you may be asking, well, why do I care about this? But it turns out that in the process of determining exact values, you go through sort of an iterative process. You first figure out what sign it is, then you figure out what its numerical value is, and so the sign, the SIGN, is the first thing that you have to kind of determine about the trigonometric function of a special angle. So here's the mnemonic. Have this sort of coordinate system. This is sort of a visual representation. And here's the mnemonic is actually these words. All students take classes. Okay? And what this is telling you is that in quadrant 1, all trig functions are positive. In quadrant 2, the sine function and its reciprocal cosecant are positive and everything else is negative. So sine is positive, and you can see that back from quadrant 2, right? That's y over r. The cosecant is r over y. Since there is positive number over positive number, it's a positive number. So sine and cosecant are positive in quadrant 2, but nothing else is. In quadrant 3, tangent and cotangent are positive. Everything else is negative. And then finally, in quadrant 4, cosine and its reciprocal secant are positive. Everything else is negative. So this is, I've heard this for 30 years. This sort of all students take classes because it sometimes is very hard to remember. Well, is that supposed to be positive? Or that's supposed to be negative? It's sometimes easier to figure out what its numerical value is, but the sign, the SIGN, is maybe a little tricky. So just recognize that this is a mnemonic, which means it's a tool for memorization. It doesn't imply anything above and beyond just a categorization. There's no magic to this. It just happens to be the way things are. So it's a way to organize the information. So like I said, at some point in the future, you're going to have to be able to pretty much from rote memorization, be able to say, well, what's the sine of 150 degrees? Well, the first thing you're going to note is that 150 degrees is a quadrant 2 angle and it's sine, so it must have a positive SIGN. Or, you know, what's the tangent of 225 degrees? Well, 225 degrees is an angle in quadrant 3, so tangent's positive, and then you use a next step to find what the actual value is, which is also memorized. But the way that you start is in quadrant 1, and then you work up from there. So that's kind of the first thing that we wanted to talk about. The next, and these, like I said, 1.4 is kind of a whole big grab bag of stuff. So I think what I'm going to talk about now is the range of these functions. So 1.4, page number 2. So the ranges of the functions. So first thing to note, if you look at sine, so remember sine is of any particular angle is defined as y over r. Now it's important to note that sine can be both positive and negative and 0, and we've seen that with quadrant angles. But it will never be the case that y is actually larger than r. It can actually be equal to r, or it can be its opposite, but it can't be larger in magnitude because you know, that's kind of what's called the triangle inequality. And this leads to the idea that no matter what angle you pick, sine of theta is always going to be between -1 and 1. Okay. Now, if you use some notation that maybe I'm sure you're not familiar with, but it's a little bit of shorthand. I'm pretty adept at using some more complex notation, but if you imagine that you have a function of functions, and I'll use this repeatedly so that you get a little more familiar with it. But this RAN function takes functions and spits out their ranges. So this is a set, or sorry, this is a yeah, it's generally the set of a function. It is in fact the range, but the shorthand way of, you know, you can also use a DOM function, which is the domain. But you'll get more familiar with this as I do it. I'll kind of do it side by side, and then I'll simplify it to this. So basically, you can have any number between 1 and -1 as an output for sine. Remember, these two statements here are kind of equivalent, right? When you say that a variable or a function of a variable is between -1 and 1 inclusive, it's equivalent to this interval. All right, so the range is that interval. Similarly, if you think about how cotangent work or cosine works, it's the same sort of thing. It's between -1 and 1. So the range of the function cosine is this closed interval -1 to 1. Now, those are pretty easy. Let's think about tangent for a second. Remember, tangent of theta is y over x. Now, depending on what the angle is, it would be possible for x or y to be positive or negative. We know that tangent also can attain a value of 0. In fact, all trig functions can. So is there any value that is restricted for tangent? I mean, you could think, for example, maybe like an angle that's really, really close to 90 degrees, but not quite there, where y is a very, very large number and x is a very, very small number. And so tangent of x could get to be extraordinarily large. There's really no limit on it either. It can just get as big as you want, at least in the positive respect. And that also applies in the negative respect as well. So as it turns out, tangent is unbounded. It can obtain any real number. The range of the tangent function is any real number, and the way to write that is range of tangent is equal to the open interval -∞ to +∞. And just I know this is kind of a little bit silly, but this cannot be closed. Infinity is not a number. It's a concept. And if you ever find yourself in a math class where you're actually including the symbol infinity in the real number line, congratulations. You've made it. You've made it to the top. Okay, so those are kind of the quick and easy ones, but we could very rapidly make the same argument for cotangent, because it's kind of the reverse situation where it's x over y. So the range on cotangent is going to be exactly the same as the range on tangent. It pretty much can obtain any real number as an output. Okay, so what about the reciprocals of sine and cosine? Okay, so let's take a quick look at that, because that's a little bit, I mean, it turns out that they're the same for, like, you have these pairs. Sine and cosine have the same range, tangent, cotangent have the same range, secant and cosecant will have the same range. But let's just look at one specifically. So recall that secant of theta is the reciprocal of cosine, so it's r over x. So kind of the exact opposite of the sine situation. It's possible for these to have different SIGNs, right? R is always going to be positive, but x could be negative or positive. But note that x will never be larger than r. It can be equal to r in magnitude. So it's possible for these functions to attain the value of -1 or +1, but they can't obtain a value that's closer to the origin, right? So this is a situation where the magnitude, or strip the sign off of it, secant can be larger than 1, and it can equal 1, but it can't be smaller than 1. All right, and so the range of secant actually happens to be the union of two intervals. So it's any arbitrarily large negative number up to and including -1, together with any arbitrarily large positive number, 1, or any larger number including 1. Okay, and cosecant, which has the same sort of properties, except it's r over y, has exactly the same range. So any arbitrarily small number up to and including -1, together with 1 or any larger number. Okay, so this is not super critical, but I think there are some questions in the homework that ask about this, but this is a quick way to check. I mean, if you're doing something with your calculator and you type in an angle and then you hit sine of that angle, and you end up with a number like 2.7, well, you've obviously fat fingered something. So you have to be cognizant of the fact that you can't have values that are outside here, especially when we start working with inverse functions, because it's like, well, the range is restricted, so the domain of the inverse function is likewise restricted. Now, I think that's kind of maybe an okay stopping point for this first segment. I'll pick up here with a sort of tangential topic, because I want to start something that's actually going to probably take a minute. Well, I mean, I think this is sort of a sideline, but we'll come back to developing what are called the Pythagorean identities, and then we will use some of those in a sort of interesting way. So I will see you in the next.